In this video, we're going to explore Hugging Chat and demonstrate how to use various prompts to get various answers. Hugging Chat is a generative AI model similar to ChatGPT. However, there are some differences with Hugging Chat. One of the major differences between Hugging Chat and other prominent generative AI models is that Hugging Chat is open source. This means that unlike its proprietary competitors, we can go in and examine the source code of Hugging Chat and see exactly how it works. This also means that as an open source project, users are able to access and modify the source code of Hugging Chat in order to continually improve and add new features as well as fix existing bugs. Now, Hugging Chat is also not nearly as mature as something like ChatGPT. So the results and the outputs that you get from Hugging Chat may not be as reliable as some of the more well-known generative AI chatbots. Another differentiator that Hugging Chat has is that we don't need to be logged in or to create an account before we can use the chatbot. We can use Hugging Chat anonymously without being signed in. To get started with Hugging Chat, open up a web browser and navigate to the URL seen at the top of my screen. https://huggingface.co/chat. When you navigate to this website, you'll be met with the Hugging Chat landing page. Before we get started with asking prompts to Hugging Chat, we can see that it gives us some information about the model itself. In the upper right, under the current model header, we can see that Hugging Chat is running meta-llama/llama-2-70b-chat-hf as its current model. And if we want to get more information about that model, we can click the website button in the bottom right of that current model window, and that will lead us to the website for the Llama model. Here we can get more information about the Llama model that Hugging Chat is using. But for now, let's just stick to the Hugging Chat webpage. When we're ready to start asking some prompts, we can go to the bottom of the page and click in the text bar that says Ask Anything. We have a few examples given to us on this page as well. In the middle of the page, there are 3 examples. 1. Write an email from bullet list. 2. Code a snake game. Or 3. Assist in a task. So let's try these examples. I can click on the first one, Write an email from bullet list, and it starts to generate some answers. And now the generation of our prompt is complete. So we have in front of us an output box that is generated based on the input that we used. So the input that was used by Hugging Chat for our example was, as a restaurant owner, write a professional email to the supplier to get these products every week. 10 bottles of wine, 24 eggs, and 12 loaves of bread. And then based on this prompt, Hugging Chat has created and crafted that email for us with fields that we need to replace ourselves denoted by square brackets. So for example, we have Dear Supplier's Name at the top of the prompt. It's expected that we would replace this with the name of the supplier that we are emailing. These square bracket replacements are present throughout the entire generation, so we need to make sure that whatever we are generating and using, we parse through ourselves to replace the relevant information. It's also interesting to note that as the generation happens, there is a delay with the generation. It doesn't all come as one big block. And that's because every word is generated individually. For every word, the model goes through and calculates what the most likely word is going to be in that location based on the word or words that have come before it. And then it repeats its process for the next word and the next word until the generative process is done. And this is why we see the delay as each subsequent word is calculated. Now I'll click back on my browser to go to the next example, and let's click on Code a Snake Game. And now in this case, our prompt is code a basic snake game in Python and give explanations for each step. The prompt can be seen at the top of the window, and now we are getting programmatic step-by-step output of how we can code that snake game. And it gives us the steps in order, going from importing the necessary libraries to initializing Pygame, all the way through the process of creating a snake game in Python. And now that the generation has finished, we have a complete step-by-step guide as to how we're going to go about creating this snake game in Python. This can be very useful if you're trying to learn a new programming language or a new programming idea. Once again, I'm going to hit back on my browser and go back to the main screen and click on the third example, which is Assist in a Task. And the output that we're using now is, how do I make a delicious lemon cheesecake? Which can be seen at the top of my screen once again. And at this point, the generative AI is creating a recipe for a lemon cheesecake. And now that our generation is finished, we have a recipe for creating that cheesecake. However, this brings up a good point to consider when working with generative AI. There is no guarantee given by a generative AI that the output that it is presenting to you is correct in any way. This is especially important in this particular case where we're dealing with a physical process. The generative AI might produce a recipe and procedure that is dangerous. There is no guarantee that the ingredients it tells you to use will mix properly or will be used in a safe way, and that the procedures that you're supposed to follow are safe for use. So it's very important that we don't take everything that the generative AI says or outputs to us as fact. We need to parse through ourselves and make sure that what it is telling us to do makes sense and is safe to do. So for example, we see step 1 is preheat your oven to 350 degrees Fahrenheit. This seems pretty reasonable, but what if it had said preheat your oven to 800 degrees Fahrenheit? Well, this is significantly hotter than most ovens are supposed to go or generally go. And as a result, if you followed the instructions without parsing it yourself, you would put your oven and your house into a dangerous situation. So it's important to understand this fundamental concept of generative AI, that it does not produce you with a correct answer. The chatbot will always give you an answer, but it will not always give you the right answer. So these are some of the ways that we can use generative AI to get ourselves some output or some answers to various questions or requests. For the most part, all generative AI works fairly similarly. So whether you're using Hugging Chat or ChatGPT or any other generative AI chatbot, you will interact with it in very much the same way. In this video, we're going to show how we can use AI to enhance an existing security tool or process. For this demonstration, we'll be using a hypothetical scenario where our network analysts want us to train an AI model to help them identify malicious behavior in packet analysis and log analysis procedures. And specifically, they want our AI model to identify UDP-based DDoS attacks. Now, to train our AI model, we're going to be using a dataset available from the University of New Brunswick. To access this dataset, navigate to the URL seen at the top of my screen in the URL bar, https://www.umb.ca/cic/datasets. And then on this page, scroll down under Available Datasets and expand the list underneath IDS Datasets. And then we'll click on DDoS Evaluation Dataset, which takes us to this page explaining everything we need to know about the dataset. And if we scroll down to the bottom, there's a link to download the dataset. So this is where you can get the dataset that we're using in this demonstration. However, as with anything related to malicious behavior, exercise extreme caution when downloading files from the internet, and make sure that you do your due diligence on anything that you're trying to source, even if it is from a reputable provider, before bringing that into your own environment. In this demo, we will be working in a Windows system, so everything we're doing is going to be in a Windows PowerShell window. Once you have your Windows PowerShell window open, we'll need to start up Python. To check whether or not Python is installed on your system, type in Python and hit enter. If an interactive terminal starts up, giving you the Python version and the triple chevrons indicating the interactive environment, then you have Python properly installed. Next, we'll need to install some packages or libraries that we need to work with in order to train our AI model. The first is scikit-learn, which is the machine learning library that we'll be using. To install that, we use the command pip3 install -U scikit-learn and hit enter. Next, we need to install the pandas library, which is how we're going to work with our dataset. Once again, we'll use pip3 install -U pandas. Now let's start building our model. So to do that, we'll start up our Python interactive terminal once again with the command Python. And now we're going to import our required libraries. So I'll import the following libraries. Import pandas as PD. I'll import numpy as NP, which is going to help us when working with our arrays. Then from sklearn, I'm going to import the pre-processing library to help us with normalizing and processing our data. Next, I'm going to import train-test-split from sklearn.modelSelection, which will help us with dividing up our dataset into training and testing sets. Next, I'm going to import logistic regression from sklearn.linearModel, which is the algorithm that we're going to be using to train our model. And we'll be using a classification style algorithm in order to decide whether a given piece of traffic is malicious or not. Next, I'm going to import the Jacquard score from sklearn.metrics, which will give us a way of evaluating the accuracy of our model. And now I've just cleared my screen to clean things up a little bit so that we can go back to the top of our terminal. And we're going to import one final library, which is classification report from the same sklearn.metrics library. And now we're ready to get started with our code. The first thing we'll need to do is read in our data into a variable. Our data is saved as a CSV format, so we're going to use the pandas library to do that. So I'm going to call my variable mal_df equals pd.read_csv. And now I'm going to be passing it a Windows file path, so I'm going to preface this string with the letter R, double quotes, and then the path to wherever your data set is stored. And then close the double quotes and close the bracket, and hit enter. And this will read that CSV file into a data frame for us. Now that our data frame is loaded, we can take a look at what our data looks like. So I'm going to just type in mal_df into the console and hit enter. And now this is showing us our first few rows and our last few rows in the dataset. And then along the top, we have the column names. Now there are about 80 columns in this dataset. So once again, the data is truncated and only showing us the first few column names and the last few column names. If we want to see the shape of this data, we could call mal_df.shape. And it tells us how many rows and columns are in this dataset. So we have 3,782,206 rows in this dataset and 88 columns. Now we're going to need to pare down how many columns or features we actually use in our training model because we're not going to be using every single column. Oftentimes, not every feature is going to be relevant to what you're trying to train, so we're going to pare down only the features or columns that we consider to be relevant to our model. So let's take a look at what all of the columns are, and we can do that by calling mal_df.columns. And now we have a full list of all the columns or features in our dataset. So from this, we're going to pick a subset of the features that we want to use to train our model. An important point here is that, annoyingly, some columns, such as flow ID, start without any white space, but some columns like source IP start with one character of white space before them. So it's important that when you're specifying the column, you know whether the column has white space before the text starts or not. So to pick our dataset features, we're going to pare down the columns. We do that by saying mal_df equals, and we're going to set it equal to mal_df, square bracket, square bracket, and now the list of features or columns that we want to include. In this case, we're going to include source port, destination port, protocol, total forward packets, total backward packets, flow bytes per second, flow packets per second, and label, and then close it with 2 square brackets. This last feature that we chose, label, is actually what our AI model is going to try to predict. This label is going to tell us whether something is malicious or not. So now that our dataset has been pared down, let's take a look at it again by calling mal_df. And now we can see that all of the columns are present, and we've removed a significant number of them. So all of the columns that we specified are now present in our dataset: source port, destination port, protocol, total forward packets, total backward packets, flow bytes per second, flow packets per second, and label. And all of these columns, except for label, are going to be used to predict the label. Now, if you remember back to our hypothetical scenario, we decided that we're going to specifically train for UDP-based DDoS attacks. So in our case, anything that's labeled as UDP, we're going to classify as malicious. So we're going to convert that into a numerical value to allow our AI model to work with it. So what we'll do is we'll specify anywhere that there's UDP present, we're going to change that to the number 1, indicating malicious. And if the label is anything other than UDP, we're going to label it as 0, or not malicious. We'll type in mal_df, and then we're going to pass a few values to this replace function. The first is to_replace, and we're going to set that equal to UDP. And then we're going to specify value, and we're going to set that equal to 1. Then we're going to specify inPlace equals true to make sure that it does the actual replacement on our variable. And we'll hit enter. Now, let's take a look at our dataset again by typing in mal_df. And if we look over in the far right on the label column, we can see that anywhere that there was UDP before is now the number 1. Our next step is to replace all the other values with 0. So to do that, we'll type in mal_df, specify the label column, and we'll set that equal to pd.to_numeric. And as arguments to this function, we'll pass in mal_df label column, and we'll set errors equal to coerce. Then we'll call .fillNA 0, and finally we'll call .astype int. And so what this is going to do is go through our label column, and anywhere that it finds a value that isn't a number, it's going to replace it with a 0 as an integer. So now let's look at our dataset once more by calling mal_df. And we can see in the label column on the far right, all of our values that were not UDP are now 0. So we're almost there in terms of our data, but now we see that in the second row, under flow bytes and flow packets, we have infinite values. So now we need to get rid of those infinite values so that we're only working with numeric values. To do that, we're first going to replace all of our infinite values with not a number values. And we'll do that by calling mal_df.replace once again. And we're going to pass it a list of both infinite and negative infinite values, which we specify as np.inf and negative np.inf. Then we'll specify np.nan, which is the value that we want our infinite values to become, which stands for not a number. And once again, we'll set inPlace equal to true. Let's look at our data set again with mal_df. And our infinite values under flow bytes per second and flow packets per second are now not a number. At this point, we can drop all the not a numbers using the drop_na function on our data frame. So to do that, I call mal_df.dropNA, and I specify inPlace equals true again. And the values that we wanted to be removed have been removed. Our next step is to define x and y for our data set. X will be our features that we use to predict, and y will be the label that we are trying to predict. So first, I'll list out our columns using mal_df.columns, and then I'm going to specify x equals np.asArray, mal_df, square bracket, and I'm going to paste in all of the columns except for label, and then close it with a square bracket, and a round bracket. Next, I'm going to specify y using the same method, y equals np.asArray, mal_df, square bracket, and then we'll pass the label column. Now we want to normalize these values, so we'll use the preprocessing library for that, saying x equals preprocessing dot standard scalar dot fit x dot transform x. And now if we look at our array, we can see that the values have been changed to be normalized. Now we need to split our data set into training sets and testing sets. So to do that, we'll type in x_train, x_test, y_train, y_test, and set that all equal to train test split. Then we'll pass in x, y, a test size of 0.2, and a random state of 4, and hit enter. Now we can look at the various shapes of our training sets and our testing sets using xtrain.shape and ytrain.shape, which shows the respective values in terms of rows and columns in our training data set. In this case, 2,964,127 rows, and we could do the same thing for the test set as well if we wanted to. So now let's create our logistic regression model. We'll call it log_reg, and we'll set that equal to logistic regression. We'll set our C parameter to be 0.01, which is a regularization parameter, and then we'll set our solver equal to liblinear, which is a numerical optimizer parameter of which there are various values, and we'll fit it on our training sets, xtrain and ytrain. And hit enter. So now we have our model trained on our training sets. Now we can start to make some predictions with our model. So we'll call our predictions y_hat, and we'll set it equal to log_reg.predict, and we'll pass in the testing set, xtest. Now, if I want to see the output of y_hat, I can type in y_hat, and it gives us an array of values. In this case, anywhere that we see a 1, it means that the model has detected that that particular network packet or network transaction is classified as malicious. Now let's take a look at the Jacquard score of our model. So we call Jacquard_score, and we pass it ytest, yhat, and pause label equals 0. And we can see a Jacquard score of 0.44. Now that's not a very good score, but we also just picked the features randomly, and we didn't put a lot of thought into how we're training our model in particular. So there is a lot of room to improve the accuracy of our model. Some of the ways that we could improve the accuracy of our model is we could go back to our feature set and pick out more or better features. If you remember, we pared down the first feature set fairly arbitrarily. So if you did more research to see which features have the higher weighting and are more critical to the prediction model, you could improve the accuracy of the model by including or excluding different features. You could also tune the values of your algorithm or use a different algorithm. We used a logistic regression model for classification, but there are also other options that might fit the data better. So it's important to realize that there are many different variables at play when working with these AI models, and you need to iterate with the model to get the best possible accuracy that you can. And finally, let's look at the classification report. So I'll print classification_report, and I'm going to pass it ytest and yhat once again. And now here we have values like precision, recall, F1 score, and support. This gives us further accuracy about our model. So now we have developed an AI model that is able to look at network packets and network packet data and decide whether or not those packets represent malicious behavior. And the way that we could improve the security process is hand this model off to our security analysts, who can then use it to correlate with the network packet that they're looking at and see what the model's interpretation of that network packet data is, potentially allowing them to focus in on a smaller subset of that data that is more likely to be malicious.